We'll talk today about free probability eventually. So that's the lecture number 3. So we'll have 4 lectures now about free probability. This is just the first one. So we'll talk a lot about operator algebras, which are the main motivation for doing free probability. That's going to be half of the lecture, and the other half will be free probability definition, basic things, and as a first result, we'll prove a free analog of the central limit theorem, making the link with the Wigner's work on random matrices. That's going to be very interesting, but at the end. So let's find this presentation first. Here we go, operator algebras and free probability. So it's a mixed lecture, very basic things on both topics. So the plan, as I was telling you, first operator algebras, which can be of 2 kinds, C star and von Neumann. We'll see that von Neumann. We'll see that in a second. Then free probability, basic things. And the very first basic result of Voiculescu is the R transform, which linearizes the free convolution. And with that, we can put the CLT and get applications to Wigner matrices. So operators, well, we're interested in linear bounded operators on a Hilbert space. That's what's come out somehow from quantum mechanics. People like John von Neumann decided to study these operators. So we'll still follow them. How many? Almost 100 years after. So take a Hilbert space, which basically that's L2 of n. I mean, that's the unique separable Hilbert space. That's the important case. And we consider linear operators which are bounded in the sense that the norm is bounded. The norm is, of course, sup over vectors of norm 1 or smaller than 1 if you want of t of x in norm. Now, what can we say about these operators? So they form a complex algebra, B of h. B stands for bounded. That's the first thing. So they why is this true? When I say complex algebra, I have to check there are a few things that B of h is stable under sum, composition, and multiplication by scalars. Everything comes from estimating norms. So it's one-line proofs for everything. Now, what can we say about B of h? Is this algebra is very interesting, has many properties. So first, it's complete with respect to the norm. It's a so-called Banach algebra. Why is this true? Well, if you take a Cauchy sequence, then you have pointwise limits, right? I mean, this t and x will be Cauchy in h, which is complete. So we have the limits, and then you just have to check that the convergence is okay. It's not complicated. Also, you have an involution. It's exactly as for matrices somehow. You see, you have the adjoint matrix, and here the same formula as for the matrices gives you an involution. So any operator t in B of h, you can associate an operator t star in B of h. By this formula over here, the correspondence is linear anti-multiplicative. I mean, it's an involution. So is this true? It's exactly as for matrices. So if you want, you see this phi of x is tx scalar y. It's of course linear in x. So it should be the scalar product of x with something. That's something you call it t star of y. So y goes to t star of y. Now you have to check a few things that it's linear. I mean, it's clear. Bounded, it's clear too. I mean, norm of t is norm of t star. You do some computations and you get to that. And then you have to check these formulas for s plus t star and is a star plus t star, and also the product. Everything comes by uniqueness from here. And it's just one checks for everything. And finally, so this is somehow very, very simple. Now there's something a bit more tricky, which takes, I don't know, a few lines, like maybe 4 or 5 lines. I struggle with it in the beginning if you're not used to that. So the norm and involution are related by this tricky formula here. T star in norm is norm of t square. Why is this true? For matrices, for instance, the norm is the biggest eigenvalue, right? So on both sides, I have the biggest eigenvalue, absolute value square. Well, here we can't use such a proof. I mean, I don't have eigenvalues for operators, so I have to struggle with this scalar product of the definition. This formula over here, and you prove it by double inequality. It's not very long. It's, let's say, a quarter of a page. Very good. So if you have a complex algebra, which is complete, has an involution, norm involution related by this formula, now I can define our operator algebras. it's more or less inspired from the definition of B of H. So this coming to flavors. So sister algebra is an operator algebra which is norm closed and also stable under the involution. And for Neumann algebra is also an operator algebra which is now weakly closed and also stable under the involution. So weakly closed means that you see it's stable under pointwise limits if you want. That's obviously weaker than being norm, no, it's stronger than being norm closed. So the basic examples of this, so this is beautiful, but what's the relation with probability, right? So here it is. So the basic examples of operator algebra, system for Neumann, are those which are commutative. And to be more precise, you take a compact space, let's say C of X, compact measure space. C of X, you can always represent it on L2 of X by multiplication. You just take the representation to any F here, you associate operator which to G associate FG. It's just multiplication. So this is a sister algebra, okay, C of X. Same goes in the von Neumann case, but here the algebra is a bit bigger that you can define because you can it's a bit bigger. The weak topology being stronger than the norm topology, and well, you can do it with an infinity function, okay? Now, well, the relation with probability is that this is you can prove the converse. Actually, we'll get into that in a second. So the commutative sister algebra are in fact exactly the C of X's, and the commutative von Neumann algebras are exactly the infinity of X's. So in general, you can think of any sister algebra as being C of X with X kind of non-commutative space, and then if von Neumann algebra, infinity of X with X being a non-commutative space. So you have there your non-commutative measure spaces. You can do all kinds of probability, free if you want, also classical of course, but free. So that's the motivation. But before that, well, we have to learn a bit how to deal with these algebras, right? So that's our first purpose now. So in order to do that, well, we have to take the inspiration from matrices. I mean, now we have there Hilbert space operators over it. When the Hilbert space is here, these operators are just matrices, eigenvalues. So now in general, the idea is to somehow emulate somehow that eigenvalues theory up to the point where it's possible. So that's the so-called spectral theory. And well, here are the main definitions and main results. So let's call spectrum of an element a set of lambda complex such that a minus lambda is not invertible. That's a kind of eigenvalue, right? For matrices, you get exactly eigenvalues in this way, but not the individual eigenvalues, the set formed by them. That's the subtlety. We don't have eigenvalues to have the set formed by eigenvalues somehow. I mean, we don't have multiplicity, things like that. It's just a basic set without multiplicity. Let's also define the spectral radius to be the radius of the smallest disk containing the spectrum, center at 0. So with this, here's the theorem, which is very important. So spectrum of a normal element is on the unit disk. The spectrum of a unitary is on the unit circle. Self-adjoint, we get something real. And also the spectral radius of a normal element equals its norm. So is this true? Let's take a look for the matrices. All this is very basic stuff because, of course, a normal matrix, the spectrum eigenvalues are smaller than 1, right? Now, if you take a unitary matrix, the eigenvalues are on the unit circle, well known. If the matrix is self-adjoint, yeah, eigenvalues are real, you know that too. Finding the biggest eigenvalue is the norm. So yeah, everything is clear for math. I mean, not clear, but you know, it's the proofs are maybe complicated, but it's well known. Now, in general, well, this follows. I need 2 slides here. So, spectrum normal element is on the unit disk. Well, you just use this inversion formula. I get it. Now, 2 is about unitaries on the unit circle. Where is the function here? So that's something that's true, that you know, for eigenvalues, when you apply a function to a matrix, the eigenvalues also transform in this way. We apply the function to the eigenvalues. The same is true in general. You can prove it with a bit of algebra. So f of a spectrum is spectrum of f. So for rational functions, let's say. And by using this function z minus 1, you see the spectrum of A, the inverse of the spectrum, I mean inverse of the elements there, is the spectrum of the inverse of A. Now the inverse A is unitary. I want to prove something here about unitaries. Is A star. So at the level of spectrum, you put a bar here. So finally, the spectrum of a unitary consists of lambda such that lambda minus 1 is lambda bar. So they're on the unit circle. Very nice. Now, item 3 now, what was it about? Self-adjoint is real. Well, this follows from 2. I mean, you can pass from the unit circle to the real line via transformation, and which makes unitaries correspond to self-adjoint. So that's the function. F of z is z plus it over z minus it with t real. The t real and big for the thing here to be vertical, to have no problems. So pick a t real and big such that this f of a is well defined. And this function exactly passes from the circle to the real line and vice versa, from unitaries to self-adjoints. So just get the result from the one from unitaries. Now the final thing, spectral radius of a normal element equal its norm. This is quite tricky. So first of all, because we have an inequality in one sense, we know that the spectrum of normal elements is an unique disk that you can dilate by dilate. You get this thing here. Now conversely, I just pick something a bit bigger than the spectral radius, and I can apply this Cauchy formula in this way. You get this thing here. You apply norm taken roots, so it's a bit technical, and you get to this. So this number rho, which is can be anything a bit bigger than a spectral radius, is greater than this guy here. Now, what we want to prove is that this guy is actually norm of A. If we have that, we're done, okay? Because we want to prove the converse inequality. So how to prove that this converges to norm A? Well, we know that A is normal elements. So in case it's self-adjoint, which is even stronger, we're done, because remember A star norm is norm of A to the square. So now if A is A star, this means that norm of A to the square is norm of A squared. So these guys here, when n is power of 2, you get a stationary convergence, right, towards norm of A, or done. Now in general, in the normal case, well, the idea is that A star will be self-adjoint. So once again, it's the same argument. You get it from the self-adjoint case for normals. Very good. So that's kind of tough. Actually, the whole thing takes, I don't know, 4 or 5 pages with the full details for everything. Because you see a number of things like this, that we can apply rational functions to spectral that. So, but that's some simple algebra, but it still takes, I mean, yes, 3 or 4 pages maybe. But that's the core result on this spectral of unitary self-adjoints and spectral radius. Now this we can prove now the Gelfand theorem. So the commutative algebras are exactly C of x with x compact space. So is this true? Well, take the space of characters. That's how you recover x. If you're given C of x, you take the characters. That's exactly the points of x. So in general, given an algebra like this, you just take the characters, topology on it, making the continuous evaluation maps to get a compact space. And you also can evaluate eugeromorphism like this. We want to prove that this is an isomorphism. And what was clear is that it's isometric. This follows from the spectral radius formula, okay? Also surjective from Stone-Weierstrass. So you would say that, well, we're done, but we're not done yet. You have to prove also that it's involutive. And this is a bit tricky, so you can, well, it's as for complex numbers of matrices, you have real and imaginary parts, right? For operators, you have a simple formula. So it's enough to prove it for self-adjoints, but this follows from the fact that the spectrum of self-adjoint is real. So that's somehow the idea. So we used, finally, let's go back. We used this thing here with reals, also a spectral radius, so we really use the full power of this. I mean, this Cauchy formula, everything is inside here in the proof of Gelfand here. involutivity, and here for isometric, where we use the spectral radius. Very good. Now that's the first term of assist algebra, so very important. This tells that in general assist algebra corresponds about to a non-commutative space. Very interesting. You can do non-commutative geometry if you want, or non-commutative probability, non-commutative everything, right? Now the other important theorem is that, well, if you take assist algebra but abstract, I forgot to say it here. I mean, just an abstract assist algebra means abstract Banach star algebra with the norm and an evolution, which are related by this tricky formula: A star is norm of A to the square. This actually appears as a complete C-star algebra. So is this true? Let's take C of X. So C of X, as I told you, that's it's an abstract C-star algebra, right? With the, so what are the norms? That's the subnorm of the functions. The evolution is putting a bar, but it's also concrete C-star algebra, as I told you. So because you have this representation as operators on 2 of X. Now, given an abstract C-star algebra, well, you can do the same thing. I mean, I just need to construct this L2 space, and then you use the same formula. And the L2 space, well, we cannot really talk about the measure, right? I mean, you know, that non-commutative space doesn't have points, but we can talk about integration. So what we need for constructing an L2 space is just an integration functional. And, well, you construct something like this, a linear form with suitable properties, and then the space and the representation. Very good. So that was C-star algebras. Now let's get into von Neumann. So I recall the definitions are a bit different. They must be closed under the weak topology. And in relation to what we've seen so far, of course, if I have dimensions, that's the same as C-star algebras or the star algebras. In the topology doesn't matter there. Everything is closed. And also the algebras and infinity of X represented on 2 of X, which are commutative. Now, conversely, with a bit of functional analysis operators here, you can prove the converse of this. So the commutative von Neumann algebras are exactly the infinity of X. With the small remark here that the statement involves a zero multiplicity, if you want to be correct, because H is not, can be bigger, of course, than L2 of X. You can always amplify by something. So there's a bit of theory here, but that's basically your result. If you just take, are interested in the algebra itself, the isomorphism plus, if you want, that's an infinity of X. If you're interested both in the algebra and the embedding to be of H, there's a bit of work there to be done. So, so that's all stuff to von Neumann, Murray von Neumann, who studied this, and it's very interesting because in general, the algebra is non-commutative. You can say that you have some kind of non-commutative probability that you can do there. But before that, once again, let's see what can be said about these algebras. We'll use that later. So the first thing is the bicommutant term of von Neumann. The thing is that, yeah, the condition of being weakly closed for an operator algebra is the same as being equal to the bicommutant. So that's a very interesting result because it shows somehow that the von Neumann algebras appear as commutants. If you're a commutant, if you take the double commutant over commutant, so there's three commutants equal to the commutant. So you see, when defining von Neumann algebras in this way, you can forget about weak topology. All that is just commutants, and that's important. I mean, in physics, that's how things appear in quantum mechanics somehow as commutants. Now, another comment is that, of course, von Neumann implies C-star. Now, conversely, how to locate the von Neumann algebras and C-star algebras? Well, these are exactly those having separable predual. It's a bit technical. The final as the last thing in the commutative case, we can try Gelfand to infinity of X. So is it true that this is C of some compactification of X? And the answer is yes. Yeah, that's the Stonchech compactification. So as you can see, all this is delicate functional analysis, separable predual Stonchech. So yeah, you can go further into that. Let's not do it. I think that's enough. And let's go to more and more fun stuff. So first in finite dimensions, there we have this theorem. So any star algebra is a direct sum of matrix algebras. It applies both for C-star and von Neumann. These are the same thing in finite dimensions. Was the idea where they compose one as sum of minimal projections, and this projection determines a matrix block. And that's your sum. Okay, so very simple. No, what else can we say? Well, in the same spirit, but more complicated, is the reduction theory of von Neumann. So take a von Neumann algebra, and remember, finally, the only tool that we have is that the commutative ones are an infinity of x. So you an arbitrary one, how to construct a commutative one? Well, you take the center. So you take the center, you write it like this, and von Neumann discovered that the whole algebra decomposes as an integral of algebras. Very beautiful. And these algebras, of course, have trivial center because you kill the center. These are the so-called von Neumann factors, the von Neumann algebras with trivial centers. So proof is very complicated. Functional analysis, it's a tough paper by John von Neumann. And as an example, well, what we had before in finite dimensions, that's your algebra, and that's precisely the decomposition of sum of factors. It's integral. Discrete integral means sum. So that's the idea, but in practice it's difficult. Now this, if you want to look a bit, try to understand how this von Neumann algebras are, you're getting into factors. So let's try to understand factors now. So these were, there's a long story here. So these were classified by Marian von Neumann into three classes. First we have type 1, these are the matrix algebras, and B of H itself, it's a kind of limit somehow. Then we have type 2, which is very interesting. So these are the infinite dimensional factors having a trace. There's the importance in the trace. These are the so-called type 1. And also once you have a type 1, you can always tensor it with B of H. That's type 2 infinity. I mean, if you tensor it with Mn of C, you will still get 1, right? Because MnC has a trace. But if you tensor with B of H, you get something different. That's called type 2 infinity. And finally, it's type 3. So these are the guys left. And Marian von Neumann had no idea how to deal with this. So they just left it like this. These are type 3. And what happens is this was solved a big problem. This was a big problem for a long time, solved by Alan Kohn in the early 70s, based on ideas of Tomikita, Takesaki, and others. And somehow he proved that these things appear more or less from two factors, always via some kind of cross-product constructions. So when you look at this, yeah, there's a lot of work involved. Yeah, Marian von Neumann and also Kohn based on Tomikita, Takesaki. So what's the conclusion? Well, type 1 is trivial, type 3 reduces to type 2, and type 2, yeah, it's 2, 1. So it's an important factors, type 2, 1. So yeah, that's the conclusion of von Neumann algebras. It's much better than in sister algebras. If you want to classify sister algebras, you won't get this kind of results. So it's 10 times more beautiful. The theory of von Neumann algebras more advanced. I mean, of course, in sister algebras you have a lot of theory classification, but it's not somehow basic. I mean, this is basic stuff. I mean, it's basic and extremely difficult. Sister algebras, we're still lacking that kind of thing. I mean, basic and very difficult stuff. We have specialized stuff, of course, but it's not that basic. Somehow it's a bit specialized. Let's say this is not specialized at all. It's mathematics for everyone. Yeah, who want to learn mathematics, learn factors. No, we also have one factors. Can we get even beyond that? And the answer is yes. Yeah, we still have some basic theory to be learned. There's a so-called hyperfinite one factor R. So among these one factors, there's some smallest one, which is the most important one. So in case you just want one von Neumann algebra for your investigations, that's your algebra. You can spend your whole life studying this algebra. So what's the idea? So this is a discovery by Marian von Neumann. You take any inductive limit of matrix algebras, and you close, of course, weakly, you always get the same factor in the end, a certain one factor called R. That's theorem 1, so it's uniqueness. Theorem 2, due to Kohn, is that this is the hyperfinite factor. Hyperfinite meaning somehow smallest in a function analysis sense. Very tough resolved by Kohn. And theorem 3 is that when in relation with all this classification, there are hyperfinite factors also of type 3 if you want. So you have to prove somehow that they're reduced to R, and yeah, that's true. But once again, tough work by Kohn and then by Hager, who completed the last case. So yeah, once again, this is basic theory. I mean, it's It's basic theory and extremely tough. And there are very few people who read all these papers by even Murray von Neumann, especially Kohn, and these two tough papers of Kohn and also Hagerup. So actually, I didn't read all of them. I didn't read Hagerup actually. That's, personally, I read Murray von Neumann when I was a kid, and also Kohn, I read him, and then Hagerup and also Popper has a proof, but there I didn't quite understand. So but people say that it's true, so let's believe them. I haven't checked that myself, but yeah, this is very beautiful, and actually, it's such a pity that less and less people learn these things. I know operator algebras has gone into many things which are very concrete, and many young people start without learning all these things. Yeah, try to learn. It's really beautiful mathematics by very good mathematicians. Von Neumann, Kohn. These are among the best guys in the 20th century, and yeah, it's good to see what they were writing. Check from their PDF papers and read them. Okay, so this is it now. I think that's enough as preliminaries. Let's get now into probability. So, well, let's start with the star algebra. Okay, so finding all this is not really needed. So, in order to formulate the basics, you just need a star algebra with a trace. So, the trace is somehow an integration. The elements, you call them random variables. They have moments. The law, what is this functional? I mean, to any polynomial, you can integrate it somehow. With the remark that, so this looks trivial, the remark that k must be actually a colored integer. The powers are defined like this. So what's the thing? It's always star algebra in the evolution everywhere, and A doesn't commute with A star. It's not normal in general. So that's why when you're looking at moments for everything, you have to integrate various products between A and stars. So it can be A star, star, A star again. This doesn't simplify, I mean, they don't commute, so this is a colored integer somehow. Black, white, white, black, something like this. So that's our, yeah, all these moments, and also the polynomials here are, of course, non commutative polynomials. So everything is using these colored integers is best defined like this. The remark, of course, the law is uniquely determined by the moments, by linearity. So it's a classical probability, but just, yeah, you have to use colored integers instead of integers in general. No, well, that was star algebra. Now, what can we say in the system von Neumann case? So first, in the star algebra, I mean, there's no need for von Neumann for the moment. Assuming that we have a star algebra and the trace is positive in this sense here, and that A is self-adjoint, then mu A, as defined before this abstract thing, is really a probability measure. It's rather the integration with respect to such a measure. And its support is contained in the spectrum of A, very beautiful. So I remind you that this spectrum is real for self-adjoints. So you see, it's, everything is real. Now, in addition, if you assume that trace is faithful in this sense, it's somehow it's a probability measure, which is faithful. The support is the whole spectrum. You have equality here. So that was a self-adjoint case with a few modifications. Everything extends to the normal case too, if you want. So it's standard, I mean, it's just Breeze theorem, things like that. I mean, everything here, if you take a self-adjoint momentarily and normal, the system algebra generated by it will be commutative. So you apply Gelfand, so you finally need something going on the spectrum there, classical question. That's the Breeze theorem that you need there. It's not an operator algebra result, it's a classical measure theory result of this. Now, yeah, let's see an example of all this. So what's the simplest von Neumann algebra? Well, you would say R the hyperfine factor, but so let's find something simpler that we can, something simpler is, well, of course, we don't want matrices because they are too simple. L infinity of x is also too simple, so let's tensor them. It's also called random matrix algebra. It's of a good type, I mean, it has a trace, so it just tensor the rescale trace here. I mean, trace of 1 is 1 in everything here. The integration over here, so it is supposed to come with a probability measure. So this is a random matrix algebra. It's something very dumb, I mean, it's type 1, I mean, just tensor matrices with an infinity of x. And now the big theorem by Eugene Wigner in the 50s was that if you take random matrices, I mean elements inside, having IID normal entries up to a constraint m is m star. I mean, if you on the upper diagonal, its part is IID normal, the lower diagonal part is obtained by reflection. Okay. Well, when n is big, this follow the semicircle law. It's with t depending on the variance. So this is very surprising. I mean, no matter how yeah, that's it. And the proof, well, it takes like a page or two actually. The moment method, for instance, to compute the moments of these guys, you apply your big formula, and in the limit you get the Catalan numbers, which are the moments of the semicircle law. So yeah, right away, this is just calculus combinatorics. I mean, once you apply the big formula, there are some more clever proofs of this, but we don't need them for the moment. So this is very beautiful. I mean, you see, this is very simple for Neumann algebra, hides a lot of things, and you can actually spend your whole life working on these random matrices, which is actually a very good idea. Actually, that's one of the main areas in mathematics which are hot. Working on this and not bothering about anything more general, but we won't do that. That was just an example. We'll be back to these matrices at the end of the lecture. I'll show that there's something probability to be done with them. Now let's talk about free probabilities. So this was so far non-commutative probability. So some basic definitions, moments, all that, spectral measures, and that's the simplest spectral measure, someone that we can compute and get the normal price for it, as Wigner did. Well, just kidding. So now free probability, that's something more specialized. So the idea is that classical probability is built on independence, right? Or free probability is going to be built on freeness. So here's your definition. Take a star algebra with a trace. Subalgebras are called independent if this is true, yeah, of course. And free if, and this kind of alternating is the same thing, but for alternating products. See, traces are zero, implied that the trace of the alternating product is zero. So the basic examples, yeah, of course, it's algebras are independent inside the tensor product, free inside the free product. That's a motivating example, very simple. Now, this was freeness for algebras. Now, if you take two elements, of course, you take the independent or free, and the star algebras they generate are independent and free. With the remark that it depends here. I mean, if you're in a star algebra, independence and freeness is in that setting. If you're in a star algebra sense, this should be by definition the C star algebras you're working with, generated by B and C. And in the formal algebra sense, you take B and C. I mean, this bracket symbol depends on the framework. Now, let's see some more examples. So I've seen, yeah, here, algebras are independent inside tensor and free inside the free product, but that's a bit abstract. So let's do some group algebras. That's a very interesting examples. So you take a discrete group and all the group algebra of this involution. So all the group elements are unitaries. They're represented as usual by my left regular representation. That's the thing that we use all the time. This always the same representation. And then we close, okay? For the norm, we obtain a C star algebra called C star gamma, and for the weak topology, L of gamma. And these are good algebras for us because they have traces given by this formula here, very simple on generators. So why this? Well, when gamma is abelian, you get exactly the functions or L infinity functions from the dual group, which is compact. So in general, these are small group duals. Well, very interesting. Also, it's known in relation to one factors that if gamma has infinite conjugacy classes, L gamma is at one factor. Why? Because the center depends on the conjugacy classes of gamma and collapses to C when you have ICC, this condition here. And if in addition gamma is amenable, this means that gamma is somehow smallest, the factor will be smallest, so you get R for a finite one factor. Now, relation with what we're saying, yeah, that's the result, which is very beautiful. So group algebras are independent here and free inside the free products. So this follows either from in general, I mean, from what we were saying before, get this product formula, or just by checking directly and just directly the independence freeness of group elements. This is interesting because let's go back here. These algebras here, of course, they have traces. So here you have a trace, right, on the tensor product. But if you want to trace on the free product, it's a bit tricky to define. So this was, I was cheating a bit here. So I thought it was trivial, but well, you have to work out all these things and it's a bit annoying. So in the group case, there is no annoyance. I mean, this algebra is here and you just check the freeness on group elements. So this is simpler, actually. That's the simplest. This theorem is simpler than the examples before the groups. Okay, now, well, let's try to do something. So let's try to prove a kind of CLT or something like that. So remember in the classical case for CLT, you need Fourier transform, right? You need to linearize the convolution. So let's do the same thing. So first we need to talk about free convolution, then we'll linearize it, and then we'll prove CLT. So well, in the classical case, that's the definition, right, of the convolutions. We'll do both additive and multiplicative. Because the formulas, right, you take independent variables, and that's the thing. They don't depend on the choices of A and B, right? And similar in the free case, you do exactly the same definitions, but A, B being this time free. So that's your definition for these operations, which are denoted like this. So that's what Voiculescu chose. And it's not exactly symmetric because the classical additive convolution should be a plus here, but that's not, yeah, that's to remember. You have to put a plus here and a times here for probability, and you write your articles. So don't use a star inside the box. That's not the notation. Now, well, let's try to linearize this, and the result from our Voiculescu is like this. So that's the result we made. I think it was 86. Yeah, made everything started. So his discovery was, so all that we did for so far was just some abstract things. I know nothing interesting, but that's an interesting thing. So his discovery was that the free convolution can be linearized by something very simple. So that's the R transform. So the idea is that you take the Cauchy transform. This is it. I mean, it's more as the moment generative function, somehow shifted by one. And then once you have this Cauchy, you're looking for an inverse for it. And the inverse, because of this shift here, it has to start with 1 over xi, and then it's a series in xi. And that series, we call it the R transform. And the theorem is that, yeah, that linearizes the free convolution, which is very similar to the fact that log Fourier linearizes the usual convolution. So R is not exactly the analog of Fourier, but rather of log Fourier. So let's see how the proof goes. Well, it's a weird slide here, very dense. So this is Voiculescu's proof. So we use the free Fock space, which is somehow the monoid algebra, sister algebra of this monoid. That's the so-called free Fock space. The idea, you would like to use group algebras, but it doesn't work with group algebras. You have to go a bit farther to monoids, to the free Fock space, for having good models for everything. Now the point is that, well, you have some freeness things like for group algebras, and the variables of type S star plus Fs as being the shift of polynomial model all the distributions. So very interesting. So these distributions we want to model, and their convolution can be modeled by a guy like this. Now the key remark is that you take two variables like this, with the ST being two shifts corresponding to two copies of n inside the three monoids. Then these variables are free. That's something that you can believe, right? Of course, it's like for groups. But the point is that their sum has the same law as this guy here. That is somehow by doing a 45 rotations. It's a bit tricky. So now this tells us exactly that operation which to mu associates f. I mean the modeling map here. I told you that this modeling moment solves the distributions, but I didn't tell you how. So that map, the modeling map, linearizes the free convolution, because if I put f here and g here, these are free and their sum goes to f plus g. So that's the linearization map. So now you just have to compute this map. But this computation, I mean, you're no longer in the free monoid on two generators. That was just for the purpose of having this key mark here. In order to compute this map, you're just on the free monoid on one generator. So that's a billion. I mean, it's just very simple. It's commutative, and you get this, this formula here. It's a very simple computation on the proof end. Now, well, we did that. Let me talk about ISS transform too, but without proof. So here's the second paper of Voiculescu in 87, I think. He found right after that the multiplicative conversion can be linearized as well. So what's the idea, the technique? So take the Stieltjes transform. So it's like Cauchy, but it's really the moment generating function. Now it's not shifted. Subtract this one here, then invert. And then finally multiply by 1 plus minus 1. Well, that's it. Then log S linearizes the free multiplicative conversion, and that's the formula. So proof, yeah, it's more complicated by some kind of ideas. And there's a remark here in all this, we're talking about real probability measures. So it's not clear from the definition that it's well defined, the free convolution, because remember the free convolution of mu A and mu B is mu AB. So if AB are both self-adjoint and free, their product is no longer self-adjoint. You'll say that, yeah, but I don't get a real probability measure. But there's a trick here. So you see, the moments of AB is the same as moments of square root of AB, square root of A, right? Because if you take a product of such things, you get exactly a power of AB with some square roots here at the beginning and end, but because the trace is a trace, trace AB is trace BA, you can always put the square root here and you get a plain power of AB. So the moments are the same as for this guy here. So it's well defined, the convolution operation. And that's the result. Well, so we have tools now on this proof theorem. So yeah, CLT. So here's the CLT now, which there are two statements in here, classical and free at the same time. So I take variables which are either independent or free, and I decenter the same variance T. Then when it goes to infinity, the averages, in the classical case, they go to the normal law, parameter T. In the free case, they go to the semicircle Wigner law that we talked about a few slides ago, parameter T. So as is in the classical case, well, you use the fact that log F linearizes this. You compute the Fourier transform of this. You finally get to do something like this, which is the Fourier transformability. That's the thing. The free case is the same proof. You compute the R transform of this, but using the linearization property, you get to the conclusion that this should be T psi. T psi, by some calculus, the R transform of the Wigner semicircle. So that's it. So very beautiful. So that's forgetting the abstract beauty now. Maybe does this say anything new about Wigner? I mean, besides philosophy, and it says something new about the Wigner semicircle. But what about the Wigner matrices now? Can we really apply this technology? The answer is that yes. Here's Voiculescu's third result now. So given, let's take a family of Wigner random matrices now, which means, I remind you, normal entries up to the constraint that they are self-adjoint. Then the following happens. So by Wigner, each MI follows a semicircle law, right? But now by Voiculescu, that his discovery is that these matrices are asymptotically free, semicircles that you get. It's a very beautiful thing, which was new. That's his main theorem in the 80s. And the proof, well, it's a bit long, but that for Wigner, you can just prove it with the moment method, no problem, a lot of computations, you can do it. There are some more clever proofs as well. So, well, very beautiful. So I've seen classical free probability are twin sisters. Let me just look at this. It's a double theorem. You just IF here, independent free, and you just replace the measures. The assumptions of X are identical. So they're really sisters. Now, this sistership makes the Wigner law to be the free analog of the Gaussian law. Very beautiful. And also the Wigner matrices are asymptotically free. That's something very interesting and new. So, well, next lecture we'll get more into other limiting theorems like Poisson, complex Gaussian, all that. Try to see if this classical and free probability are really sisters and to which point, and we won't be disappointed. They're really very close sisters. So, see you soon.